This is sample problem 2.04 from the Walker textbook, and it covers some constant acceleration and constant velocity problem type skills, and so it's a good example of the type of problem we'd see on a test. So it's got two different moving objects, in this case a motorcycle and a car. And the scenario is a drag race, and just so you know, this would be both of them starting from rest, which is not explicitly stated here, but let's separate out the information, okay? So we have the motorcycle. Let's try it. The information for the motorcycle would be that it begins from rest. I'm just putting M for motorcycle here. So we got a lot of subscripts. I guess for both of these, we're going to say x sub 0 is 0. But, you know, it's also fine in a lot of cases to just assume that. They tell us that the rate of acceleration for the motorcycle is greater. And that's why it's taking the lead at the beginning. Okay, ooh, so that's supposed to be a meters per second squared with an S. And then it does tell us that it gives us the maximum speed of the motorcycle. And it says that eventually the motorcycle loses the race because its max speed is less than the max speed of the car. The question is the motorcycle going to reach its maximum speed? Well, yes, I guess, you know, when you reach this kind of problem, you're going to say to yourself, well, you know, how many of these numbers am I really going to use? And is some of this information just there like as background, or how much of it am I going to check at the end? So here, my assumption is that what's going to happen is the motorcycle takes the lead. It will get to its maximum speed and then have to just go at that maximum speed, while the car is going to accelerate for a greater amount of time to a greater speed. So I am going to write down the maximum speed of the motorcycle as Vmx at that 58.8 meters per second. And then I'm going to treat the motion of the motorcycle in two parts in a minute. But let's write down the givens for the car. So for the car, again, we assume it starts from rest. That's how a drag race works. It has less acceleration capability. So it cannot gain speed as quickly. Okay. I don't know if it's going to get up to its maximum speed. So I'm hesitating to write that number 106 meters per second. What I do know is that it's going to catch up, meaning that at some point in time, the car and the motorcycle will be side by side. They will have the same position at the same time. That's useful. So that I will be able to set the position as a function of time for the motorcycle equal to that of the car. But I'm going to first take the information I know about the motorcycle and solve for how long it's going to take and how far the motorcycle is going to go in its acceleration phase, because I already have enough information to go on to determine those two things. So first of all, let's say part one is my speeding up phase for the motorcycle. So let's do this. And I would like to know time. And so as I'm looking at my formulas, I do have a formula where all I need to know is the velocity at a moment of time, the initial velocity, and the acceleration, because I know these three things and my unknown is time. So I can solve for it. Let's do that. And if you got your calculator out, you can check my work here. When I do that though, divide both sides by 8.4. And I solve, and that comes out really nice and even. You can tell this is a book problem. So I get 7 seconds. And then I also would like to know, because I care about position, I'd like to know where is the car, or sorry, the motorcycle at that point in time. Now I have lots of information. So there are several equations I could use. So I just pick one. One I could use is this one. X is x0 plus initial velocity times time. This one. Oops. So let's say we started at 0 meters, like that was the starting line. And then this, just the whole term goes to 0 because it started from rest. So then if let's use 3 sig figs, so then I'm getting about 206 meters. Okay, so then that's important because now the motorcycle is going to be, from now on, going a constant velocity. And I couldn't write just one single position equation for the motorcycle because it's complicated. At the beginning, it's going to be a quadratic function, and then it's going to switch into linear. So this is really just part one, at the end of part one. So now though, now that I know that, I can write an equation from now on. Where will the motorcycle be? So for part two, that's the part two, constant velocity, but then I can include where the motorcycle is. So from part one. So now the motorcycle is the 206 plus it's now going its maximum speed, which is 58.8 meters per second, times however much time has gone by. But I need to subtract the first 7 seconds. You know, if it's second number 8, I don't multiply by 8 seconds. You know, it's only been going its maximum speed now for a total of 1 second. So I must subtract off the second, the 7. So that will predict now where the motorcycle will be anytime after 7 seconds. Okay. Now for the car, that's easier. I am assuming, again, and we'll see if it works out, that the car is just accelerating this whole time because it's slower to accelerate. So for the car, I'm predicting its position to be a quadratic function where, so we got x0, which I'm going to say is 0, but let's write out the general equation, plus for the car, and so the car's equation would be its starting point plus it, this whole term goes to 0 though, so because it started from rest and then it's got its own initial, or sorry, its own acceleration value. And I am assuming from time 0 it was accelerating. So now I'm going to set those, the motorcycle equation and the car equation, equal to each other to find out the time at which they are at the same position. And that's the part where the algebra, like the, gets a little bit ugly. But here, so I'm set them equal. Assuming same place, same time. Okay, so then now I guess I could distribute this. Maybe I'll do that in the next step. 58.8 times t minus 7. And I'm going to start getting lazy here. And then set that equal to 1/2 times 5.6 t squared. Okay, so then I'm going to get that into a form where then I'm going to solve the quadratic formula. So I get 412 when I distribute that 58.8 times -7, and then okay, then I'm going to get it, bring this over, and this ends up -206 equals 0. Okay, and then I did do this already. So when I solve the quadratic formula, I get 2 possible answers. One is 4.44. The other is 16.6 seconds. And I already solved for the time that it took the motorcycle to get up to its maximum speed, and that was 7 seconds, remember? So I know that the 4.44, there's no way the car is catching up in that amount of time. So this is the answer I'm going with. That is when the car will catch up with the motorcycle. Okay?